For trig forms of complex numbers, a lot of the work is going to look very similar to what we did with the vectors. One thing I want to remind you about from your previous algebra classes, if I have the complex number 2 plus 3i, one way that I could plot that complex number is on an Argonne diagram where the horizontal axis would be the real part and the imaginary axis, the vertical axis would be the imaginary part. So I could plot this imaginary number as 2 in the horizontal direction and 3 in the vertical direction. Okay, so actually plotting the complex number would not be the segment, it would just be the point that is right there. Okay, the distance between the origin and the point of the complex number, they call the modulus. And I'm going to say that, hey, z is that complex number. And the complex modulus is the square root of the real part squared plus, so that's a plus bi. So I'm going to call that the real part plus the real number that we multiply by the imaginary part. And this should look familiar to you. That is the Pythagorean theorem, assuming that this is a right triangle, which it is. So the complex modulus is actually the distance between the origin and the point marked on the Argonne diagram. And from vectors, when we did vectors, we also learned that the cosine of this segment, so I'm going to go the cosine of the argument of z. That's the argument of z is the angle that you would make with the positive x-axis, is equal to the real component divided by what we called in the vector component the radius, and that the sine of the argument of z is the vertical component over the complex modulus. And what that's going to allow us to do is to rewrite this in trigonometric form. Let me get a different pen for you. In the trigonometric form of a complex number is r cosine theta plus r sine theta times I. Notice I have the r, which in this case is the complex modulus. I can factor that out. And I'm going to put the I in front, so that way there's no confusion that I'm taking the sine of theta I. And that is the trigonometric form of a complex number. It's r times cosine theta plus I sine theta. And you may see this as r cis theta. Okay. So first thing I'm going to do is do the examples that are in your book. The first example I'm going to do is example 334. And they want us to find the trigonometric form where z is equal to 1 minus I. So what I'm going to do is draw it on an Argonne diagram where this is the real component and this is the imaginary. So I'm going to go 1 in the real direction and negative 1 in the imaginary direction. That's my point. I'm now going to calculate the complex modulus because I need that in order to calculate theta. So the complex modulus is the square root of 1 squared plus negative 1 squared, which is the square root of 2. And you should have already known what this distance was, because if that's 1, that has to be the square root of 2. And I need to know what theta is. Okay? So theta, it's a quadrant 4 angle. So I can represent theta in various ways. I want to represent it as a positive angle. That'll make things easier for me, and then I'm going to represent it as a negative angle to show you how this equation would work. So my r is the square root of 2, and the cosine of theta. Well, the cosine, so I'm just going to write it as the cosine, and theta is 1 pi fourth, 2 pi fourths, 3 pi fourths, 4 pi fourths, 5 pi fourths, 6 pi fourths, 7 pi fourths. Plus I sine theta, and that would be 7 pi fourths. Okay? And you should note that if I were to multiply this out and actually do the math here, I would actually get back to 1 minus I. Because we know the cosine of 7 pi fourths is 1. We know that the sine of 7 pi fourths is negative 1. And that would give me 1 minus I. And then I'm multiplying it by its distance. So I just wanted to show you how to do that. Okay, now if I would have put a negative angle in here, I could have done negative pi fourths. So let's talk about that. So I have the cosine of negative pi fourths plus I sine of negative pi fourths, all times the square root of 2. And notice that the cosine of a negative angle is just the cosine of the positive angle. So that would be the cosine of pi fourths. But the sine of a negative angle is negative the sine of the original angle. So I'd have minus I sine of pi fourths. So the reason why I always use a positive angle is so that I always have the plus sign that's represented in here, so that I don't have to worry about negative signs in here. Because this means cosine plus I times sine of the same angle. Okay? So the shortcut I could have written for this one would have been z cis 7 pi fourths. So that's the first example. Second example is 335. And they tell me that z is equal to negative 3. Well, another thing you have to remember here is that is negative 3 plus 0i. So I'm going to put little dots around here. I'm going to plot it on the Argonne diagram. And that would be this point. And I know that the complex modulus is the distance between the origin and the point. So the distance is 3. Remember, your complex modulus is always going to be positive. Okay, so my final answer here would be 3 times the cosine of, where's this angle? That angle is pi plus I sine of pi. Alternatively, I can write 3 cis pi. The next one is to approximate the trigonometric form of negative 12 minus 5i. So that's 336. Negative 12 minus 5i, we're going to approximate it. As I always draw it, So negative 12 minus 5I is this point. Okay, I need to calculate the complex modulus. This is a 5, 12, 13 triangle, or you could use the formula to calculate the complex modulus. And to approximate it, I know that the cosine of theta is equal to, they told me it's A, which is negative 12, over 13. So I know that theta, and in this case when I put this in the calculator, I am going to get a number that is in quadrant 2. But I need to transform this quadrant 2 number that I'm going to get, that's this angle right here, into a quadrant 3 angle. So I'm going to use degrees. So I'm going to take the inverse cosine of negative 12/13. And it tells me it's 157.38 degrees. So that's going 157.38 this way. Well, this is 157.38 that way. And I told you I always want to use a positive angle. So what I'm going to do is I'm going to take 360 minus the 157.38. And I get approximately 202.62. So my answer is going to be R cis 202.62 degrees. Okay, notice this time I did not write cosine of 202.62 plus I sine of 202.62. Get used to writing it in the abbreviated format and understanding that that is what this means. So I'm going to pause the video, erase the board, and go to the next examples. So for the next thing that we're going to do is we're going to learn how to multiply and divide complex numbers using the trig form. If you look at the information in the handout I gave you, if I multiply two complex numbers, I can write each complex number in trigonometric form. So in essence, Z1 times Z2 becomes R1 cis theta 1 times R2 cis theta 2. And then in the handout it goes through using your product and some formulas for trig angles. And it gives you the formula that Z1 times Z2 is R1 times R2 cis theta 1 plus theta 2. Using the same work, the quotient of two complex numbers is the complex modulus of the first over the complex modulus of the second, cis the first angle minus the second angle, or the numerator angle minus the denominator angle. So I'm going to work through the example that's already worked out in your book again, plus the one that is blank in your book so that you can see the work. So first thing I want to do is I want to draw these two and then turn them into trigonometric form. Okay, so I have -1 and then the square root of 3. So this is, if you look at it, this would be 1 square root of 3, and you should, a lot of students think, so I need this side right here. I need an, actually the square root of 3 is right here. So this is actually 2, okay? And we know it's 2 because it's a memorized angle, and this would be a 60-degree angle, or a pi thirds angle, so I know this angle right here is 2 pi thirds. Okay, and the R is 2. So this would be 2 cis 2 pi thirds. Now let's look at the 3 plus, square root of 3 plus I. That would be the square root of 3 this direction, 1 in the vertical direction. Let's draw it. So square root of 3, 1. So this is square root of 3. This is 1. Again, this is 2. And this is a pi sixths angle because the short side is opposite the 30-degree angle. So this turns into 2 cis pi sixths. So my final answer is I take the two components, multiply them together, and then I add the two angles. So 2 pi thirds plus pi sixths That is 4/6 plus 1/6 is 5/6. And the final answer would be 4 cis 5 pi 6. Okay, and let's say you wanted to turn this back into our regular trig, our regular a plus bi form. Just use that formula. So I have 4 cosine of 5 pi 6 plus I sine of 5 pi 6. 5 pi 6 is the quadrant 2 angle that's right here. So the cosine is negative square root of 3. So this would be negative 4 square root of 3 plus this distance right here is, that's 1/2. So 1/2 times 4 is 2. And then the I. So if I were to if you were to multiply these two things together using the rules we did in algebra, your final answer would be negative 4 root 3 plus 2I. Okay? And actually, this would be negative 2 root 3 plus 2I because the cosine is not negative square root of 3, it's negative square root of 3 over 2. So if you multiply it out, this is what you would get for your answer. I think it's shorter if you're in trig form, or you can turn it into trig form to multiply them out. Where it's really important, if you were to do this division problem, you would end up multiplying by the complex conjugate, and then you'd be simplifying the denominator, simplifying the numerator, and it turns into a mess. I'm using the same trig numbers as I used before, where negative 1 plus root 3I is 2 cis 2 pi thirds. Over 2 cis pi 6. So the rule says to divide the moduli, the radii, so that's going to be 1, and then subtract the denominator from the numerator. So that's 4 pi 6 minus 1 pi 6 is 3 pi 6, which is pi halves. I have no problem with you leaving your answer in that form, but I am going to turn this into the a plus bi form. So this is the cosine of pi halves plus I sine of pi halves. Well, the cosine of pi halves on the unit circle, that would be 0. And the sine of pi halves is 1. So the final answer here would just be 0 plus 1I, or I. So that's how you multiply and divide complex numbers using the trigonometric form. Next thing we're going to do is we're going to learn how to raise complex numbers to powers and to find roots of numbers using trigonometry. If you expand the multiplication property for complex numbers, raising a complex number to a power is just like multiplying it over and over again. Multiplying something over and over again is raising it to an exponent. And then we're adding the same thing over and over and over again. So that would be multiplying the number of times I add it times what I was adding. So if I want to raise a complex number to a power, I turn it into trig form, and I just do the radius to the power, and then the angle is going to shift by the number of powers that I raised it to. So what you can think of raising a complex number to a power is, let's say that's a distance of 2, and that happened to be my angle. If I wanted to square that one, I would take this angle, I would add it to it again, but I would double this thing's length. I would actually take its length and multiply it times 2. So this would end up being 4. If that was theta, this would be 2 theta. If I wanted to do theta cubed, I would rotate it another theta, and then my length would be 8. So this whole distance right here would be 3 theta. And then if I were to raise it to another power, another theta. This would be 16, and this would be 4 times whatever my original angle is. So that's what we're basically doing by raising complex numbers to powers. So first thing I want to do is turn this into my trig form. So let's draw it. 1 in the horizontal direction, -1 in the y direction. So that's a 1 square root of 2. So r is the square root of 2. Cis, and that is 7 pi fourths. Okay, and I'm going to take that, and I want to raise it to the 4th power. So that says take the square root of 2 to the 4th, cis 4 times 7 pi fourths. Okay, the square root of 2 to the 4th is 2 squared, which is 4, cis 7 pi would be the answer for this one. Well, let's think about what 7 pi is. That is 1, 2, 3, 4, 5, 6, 7. So alternatively, you could write this as 4 cis pi, and you would still end up with the same answer. And the last one, I'm going to use this type of property to end up finding all of, in this case, cube roots. I'm going to find the cube roots of 8 and then the cube roots of -27. Okay? And basically what I do is, hey, if I've got something cubed, it's equal to this type of property. So let's think about what I actually do to take a cube root. To take a cube root, what you are actually doing is you are raising something to the 1/3 power. Okay? So let's draw 8. And let's kind of talk about it. 8 is right here. So if I wanted to write this in trig form, this would be 8 cis 0. Hopefully everybody understands that this is a 0-degree angle. Okay? And what I want to do is I want to raise both of these to the 1/3 power. Okay? So that's going to give me z is equal to, I'm going to take the cube root of r. Well, what's the cube root of 8? That would be 2. And then it says cis theta plus 2 pi k over, my n in this case is 3, where k is equal to 0, 1, and 2, because n minus 1 is 2. So what I'm going to do is I'm going to put a 0 in for k, a 1 in for k, and a 2 in for k. So my roots are going to be 2 cis. Put a 0 in here, I get 0 plus 0 thirds is 0. I get 2, put a 1 in here, so that would be 2 pi thirds. And then I put a 2 in here, and that would be 4 pi thirds. An alternate way for you to come up with these second angles is, let's talk about this. This says 2 cis 0. That would be here. Every single one of these roots fall on the same circle. So they all have a radius of 2. This is my first root. Once I know what my first root is, how many roots total do I have? I have 3 of them. So what I want to do is I want to divide this circle into thirds. Okay? Well, this is 2 pi all the way around, so that would be a total of 6 thirds. Okay? So all the way around is 6 pi thirds, and I want to divide that into 3 equal segments. Okay? So I'm going to divide that by 3. Okay, so that's going to end up, that would cancel out to equal 2 pi thirds for rotation. So my next root would be here, which would be at 2 pi thirds. And then I add 2 more pi thirds to that, and I'm going to have 4 pi thirds. So you can either use the formula, or you can use the fact that you are going to have 3 even spaced points on the circle of that radius. Okay, so let me do, actually, in your book, I'm going to do example 42 instead of this one up here. Example 42 says z to the fourth is equal to 1 plus I. Okay, I'm going to leave the formula up at top. I'm going to do the same work. I'm going to draw a point, kind of figure out what I've got, and then go from there. So, I'm going to go one horizontal, one vertical. There's my point. R is the square root of 2. So I'm going to write z to the fourth equals the square root of 2 cis, and this is pi fourths. Again, why we need to know our unit circle. So I'm going to raise everything to the 1/4 power. That's going to give me z is equal to the nth root of the square root of 2. So this would be 2 to the 1/2 to the 1/4 cis pi fourths plus 2 pi k over n, in this case, is a 4, where k is this time 0, 1, 2, and 3. Okay, 2 to the 1/2 to the 1/4 is 2 to the 1/8. And so I'm going to get the 8th root of 2 cis. Put a 0 in here. That's going to be a 0 up here for this part. And I get pi fourths divided by 4, it's pi 16ths. Okay? That angle is really teeny tiny right here, and this length would be this whole circle right here would be the 8th root of 2. Well, how many total answers am I going to get? I'm going to get 4 of them. So each one of them has to be 90 degrees apart. Okay, and 90 degrees in radians is pi halves. So I'm going to keep adding pi halves to this. Okay, pi halves has 8/16. So I take 1/16 plus 8/16 is 9/16. Plus another 8/16 would be 17/16. Plus another 8/16 would be 25/16. All going to have the same radius. And that's how I use it without using the formula. The formula that I like to use in my head is I just do that part to give me the first angle. And then I figure out how much do I have to rotate to get each successive answer. Now, let's put a 1 in here. 1 would be 2 pi. Pi fourths plus 2 pi. 2 pi has 8 fourths, so that would be 9 fourths. 9 fourths divided by 4 is 9/16. So that worked. Put a 2 in here. That's 4 pi. 4 pi has 16 fourths. 17 fourths divided by 4 is 17/16. 6 pi. 6 pi has 24 fourths, plus 1/4 is 25 fourths, divided by 4 is 25 pi 16ths. So each one of these 90-degree separated angles, each one of these points would be actually one of my fourth roots of the complex number 1 plus I. So that's it for complex numbers, and we're going to learn how to play around with some of these other trig forms next week, just before your test, so that you guys can see some applications of this trig form of complex numbers.